Okay, so hopefully this one will work. So we were talking about the dot product last time, and remember there are two different kinds of multiplications of vectors, so you really can't just say product. By the way, this happens every year that I'll have students who will write, VW, and I don't know. I mean, I make a big deal about how there's two different products. We do a lot of things with the two different products. You'll never see me use this notation other than to talk about how you should not use this notation, right? Students will do this on the final exam or a midterm exam, and it forces me to not give points, which I hate. I love giving points, right? But I can't just say, oh, well, student probably knew which one was the right one. I can't do that. So anyway, please, I beg you, don't do that because it does not make any sense, and it is not obvious which one you mean, right? Okay, all right, so we've got these two different kinds of products. The first one is the dot product, defined by this formula here, and we talked a little bit about it last time. It's got some algebraic properties that are very handy, but I'm going to say unimpressive because, we could write down lots of formulas that have these properties. Where's the geometry in these properties? It's not there. Here's some geometric properties. These are why the dot product is really interesting. This is the one that we're going to make the most use of in Math 216. Notice that we have a general dot product on the left. Any two vectors equals exactly this less than or equal sloppiness. And then everything on the right-hand side is geometric. Right? So it's very geometrically natural. There is, I will admit, one unsatisfying thing about this formula, putting forward this formula as our geometric motivation for the dot product, and that is I can't point on this picture to where the dot product is. Right? There's something unsatisfying about that. If you add two vectors, first vector, second vector, I can draw, this third vector I draw here, that's the sum. That is V plus W. I can point to it. And this is not a geometric interpretation that I can say, well, there it is. That's where the dot product is. It's, the dot product's related to these two, or these, geometric features of these two vectors and how they sort of relate to each other by a certain formula that involves cosine, right? But I can't point to and say that thing. You see that thing right there? That's the dot product. This bothers a lot of students. It makes students feel like they don't, I guess I don't understand dot product, because I can't find it, right? And you just have to accept that, the dot product is kind of a weird thing. It's useful not because it is a geometric thing that you can point to, but because it relates to geometric things you can point to. So anyway, we proved it last time, law of cosines, right? Neat proof. I left as an exercise for y'all to show that this formula implies the Cauchy-Schwarz inequality on the previous page. I think that's a nice exercise. I hope you'll take a few minutes to do that. So let's do a quick application. Here's a couple of vectors. What's the angle between those two vectors? If this were a two-dimensional problem, it'd be a pretty easy problem because for each one, you can just find the angle off of the x-axis, like arctangent or something, and just subtract the angle. This would be easy in 2 dimensions. But here we have a vector that's off. It's not just in this direction. It's also up a certain amount. That other vector is over. It's down a certain amount. We're not asking for sort of a rectangular sum of angles. We're looking for a tilted angle. Right? So, hard problem until you realize that, we have this formula that relates the geometric object I'm interested in, 2 seconds, to the dot product that I know how to compute and magnitudes that I know how to compute. Yeah, question?
Is there a separate proof or reasoning why that would hold in R3?
Sure. This is... in R3, see? It's this could be this picture applies in any dimension, right? Wherever you are, you can still talk about triangles, and triangles still obey the law of cosines. Yeah, that's a great question, but it is conveniently there's a really convenient answer. Yeah. Everybody good? Okay. Very often I'll say, like, if we have a two-dimensional picture, okay, well, here's the three-dimensional picture. Okay. So we have this this formula here, and the thing that we're interested in is related to other stuff that we can compute, and there you go. So arc cosine, let me do it like this. Arc cosine of dot product divided by the product of the magnitudes. Just solve for theta in there, and there you go. And there's your answer, arc cosine of root 6 over 7. It's kind of a weird answer. By the way, students have a kind of a reflexive urge to get it in degrees, right? Or maybe radians. Radians are, that's better somehow, right? Which it is, by the way. But don't give this to me in radians or degrees, because anything that you write down in radians or degrees here will be an approximation and therefore not exactly right. Right? So arc cosine of root 6 over 7 is a perfectly well-defined thing, right? Some decimal approximation you give me is just not quite right. Okay. And right up until the point where you're actually cutting your project, right until the point you're actually building the bridge or whatever it is, and you need to actually saw through at a particular point or measure on a protractor, right up to that very moment, you don't need a decimal approximation, right? So sure, when you're actually about to build, punch that up on a calculator. We will not be doing any building in this class, right? So just leave it as arc cosine of root 6 over 7. Okay. Some related facts. Easy to see from this formula here that if the dot product is positive, let's consider that scenario. What happens if the dot product is positive? Well, if that's positive, and magnitudes are always positive, well, that means cosine theta is positive, and if cosine theta is positive, that means theta is an acute angle. Yeah? Right? Everybody happy with that? Everybody remember your trig, by the way? I hope everybody's good with all your basic trig. We're going to be using that quite a bit. Okay. So, similarly, what if the dot product is negative? Well, if that's negative, that means that cosine theta is negative. And if cosine theta is negative, then that means that theta is obtuse. So, some neat facts. A dot product, this easily computed thing, right? By virtue of being either positive or negative, you instantly know something, qualitative about the angle. So, neat fact. Related, if the dot product is 0, same argument, cosine theta is 0, and therefore theta is a right angle. Now, there is a tricky little bit that I just kind of swept under the rug there that we do have to worry about. And that is, I was applying this to non-zero vectors. It's very important for this third part to assume that you have non-zero vectors. You have to say that they're non-zero, because if one of these vectors was the 0 vector, right, then the fact that the dot product was 0 doesn't tell you anything about cosine theta, for one thing. Right? Just algebraically, you can't just cancel the zeros. And so that's one issue. Here's the other thing, and this is even a deeper problem. If one of these vectors is the 0 vector, let's go back up to this picture. Right? If this vector here was the 0 vector, there's my W, there's my V. What do you mean, the angle? What angle are you talking about? There's no angle. An angle relates to directions. V doesn't have a direction. It is not long enough to point in a direction. So the question becomes meaningless, in fact. Right? So this is a little bit awkward. You got to be real careful if you're going to use this word right angle, right? Or similarly, if you're going to say perpendicular, two vectors are perpendicular, you're talking about non-zero vectors. Unavoidably. Okay, well, this brings up another question. Do I have to actually say this every time? It's kind of annoying. And is there any way I can outsmart my way around that circumstance? And the answer is yeah. We just made up a new word. The word is orthogonal. You can talk about two vectors being orthogonal if the dot product is 0. End of story. If one of the vectors is 0, cool. Still orthogonal. I didn't say perpendicular. Right? Orthogonal. So orthogonal means either you have two non-zero vectors that are perpendicular to each other, or one vector or the other vector is the 0 vector. If you want to say it geometrically. Orthogonal has a much easier algebraic meaning. Orthogonal just means dot product is equal to 0. So these two notions, the idea of theta being a right angle, that's a geometric statement. The idea of the dot product being 0, that's an algebraic statement. These two statements are closely connected except for the, what if one of the vectors is the 0 vector. By the way, side note, there's a temptation to sort of assume, well, geometry is what we're always interested in, and therefore this is a made-up, this word is born out of laziness because we don't want to say it right geometrically. It turns out that's actually not quite right. It very often, and we will see this soon, certainly next week, very often, whether or not an angle is a right angle is actually less interesting than, again, very often, it's just more interesting whether or not a dot product is 0. So this is not a sort of inferior terminology. This is a equally interesting terminology, just in different circumstances. Okay, so anyway. Yep.
So do we still need to say that vectors are non-zero if we're not dealing with orthogonal?
Depends on what language you want to use. If you want to be able to conclude something about a right angle, yeah, they better be non-zero vectors.
Okay.
Yeah, absolutely. Yep. Just a good way to answer questions like that is just always ask yourself, what if one of the vectors is the 0 vector? Does my sentence still make sense? Right? And if it does, cool. Okay, so here's a couple of applications of dot products. The first has to do with this idea of components. If you have some vector W, right, you can talk about the direction that W defines. And then you could say, all right, well, if I have some vector V, I mean, V points in a different direction, but I could reasonably ask, okay, sure, fine, it's got its own direction. I don't want to talk about that direction. I'm interested only in this blue direction. To what extent does this vector V point in the W direction? How far is it pointing in the W direction? We have a big football game today, so there was where the ball was. This is where the guy gets tackled. How many yards did he gain? He gained this many yards. He did not gain that many yards, right? Okay. Every so often I like to throw in a sports analogy. Can't get that thing to come on. Okay, fine. Let's do that again. Okay, so we're interested in that distance. Now notice it's based on this right triangle, and that right triangle involves lengths and angles and ways that we already understand. Right, so we already have this fact. That's basic trig. Right, so the component that we're interested in relates to that distance, the magnitude of the v vector, by way of the cosine of that angle. Just trig. Yeah? Everybody happy? Okay. Then you look at this formula and say, my gosh, it looks a lot like a dot product. Almost, not exactly, but pretty close. So we pull a standard move, which is I multiply and divide by the same thing. Perfectly legal. You can do that whenever you want. Right? And now I literally have a dot product in my numerator. And that gives me this handy result that I can compute components very easily. Yeah, sure, components involve an angle. Computing angles is hard, but it involves an angle in kind of morally exactly the same way that a dot product involves the angle, so I can compute the one with the other. And while this one was hard, this one is easy. Dot products are super easy to compute. It's multiply and add. Right? So really cool fact. You can use dot products to compute components. By the way, this is a big deal in physics, which therefore means that it's a big deal in engineering. Right? So if any of y'all are engineers or physics majors, it's very important. This is also a big deal in physics applications in Math 212. which we're all part of, right? So this is going to come up hugely in Chapter 15. It's going to be a really big deal. Components are computed with dot products. Okay. Note furthermore that if the vector defining our direction, if that's a unit vector, right? Then, well, if that's a unit vector, that means that magnitude is 1. That denominator just disappears, and that leaves us with this really nice fact that if you're talking about a direction, in the language of a unit vector, which again we've already kind of talked about that. We use unit vectors to represent directions. Components are dot products. Full stop. Dot products are components. That's pretty neat. In fact, if you had to say, okay, well, how do you, where is the dot product? Can I point to the dot product? The closest I can come is saying, well, as long as one of your vectors is a unit vector that you're using for the purpose of defining a direction, a dot product is a component. For your consideration. Okay, here's another application. Physics, no surprise. I kind of gave that one away. Do y'all remember this formula from high school physics? Work is force times distance. Okay, it's not really 100% true as I sort of glossed over, stated it there. Work is equal to force times distance if the force and the displacement are in the same direction. Right? So easy counterexamples. If I say, well, how much does this stylus weigh? And okay, how far is it to the ceiling there? Okay, that's what's that, about 4 feet? Okay, this has got a certain amount of weight. And I could multiply those numbers and get an amount of work that it would take to move this stylus 4 feet. But very importantly, that's how much work it would take to lift this stylus in the direction that I am currently applying the force to keep it from falling down. If I wanted to move the stylus over here 4 feet, that doesn't take any work at all. Right? This is not work. This is nothing. Right? You could say this is me being inefficient because I'm holding it up with my hand. Well, I shouldn't be holding this with my hand. I should put this on this cart and slide the cart over. Grease up the wheels really good, right? So it doesn't take any effort, and just kind of push it ever so slightly and just watch it slowly glide over. Right? There's no work actually involved there, other than me being inefficient. Okay, so. If they're not in the same direction, then here's the modification of that formula that y'all all saw in high schools. And let me zoom back in here. So, sure, there may be this amount of force, but only the amount of the force in the direction of motion is considered. Right? So if there's a great force off in some other direction, well, we don't care about that. Just to what extent is the force in the direction that we're actually going? I think that's fairly intuitively plausible. Right? Okay. All right. Well, here's a rewrite of that component. We have a formula for that component. What is this distance? That distance is the magnitude of the displacement vector. And then very conveniently, notice that these things cancel, and what you get is this lovely new formula: work is equal to force vector dot displacement vector. So if you think about it, that's really a much more natural formula than this formula up here. This says interpret force as a scalar. Force isn't a scalar. Force is a vector. Force intrinsically has a direction that it's applying. Viewing force as a scalar, that's weird. And that's very high school, right? Because you don't know what vectors are in high school, so that's fine. And then multiply by distance. Hey, how come we aren't considering the direction? Well, it's because this is high school. That's why, so we can't talk about vectors. But if you think about it, a distance of motion, what that means is you're talking about a displacement. And displacements are naturally vectors. So this formula here, again, in the high school context, this is the best you can do, but this is forcing the user to make unnatural interpretations of these physical quantities of force and displacement, and thus get a formula that's not quite right, because it has certain assumptions and asterisks. It's just so much easier to do this and say, well, interpret the force as it is, as a vector. Interpret the displacement as it is, as a vector. The relationship between work and those two vectors, dot product. Now, there's no, unless the directions are related in a weird way, in which case we modify. No, that's the end of the story. So this is a nice example of something that happens a lot in physics, by the way, which is that sometimes the simplified versions are actually harder to understand. Right? There's more annoying details. If you just understand things in their full generality, formulas tend to be easier. Right? So viewing force and displacement as vectors, as of course they should be, easier formula. Okay. When I was taking physics classes as an undergrad, at some point, before I had the appropriate background, I was reading, how they have these books, physics for the layman, cosmology for someone who doesn't know any serious math. And I'd read some of those books, and I was like, wow, this is really complicated. This is weird, and man, it's hard to understand and so strange. And then I learned the appropriate math, and took for example, a quantum mechanics class. Quantum mechanics is a lot easier to understand if they would just say it honestly. But you read quantum mechanics for the layman, and it's like, wow, this is weird and creepy. You read quantum mechanics in real math language, and it all kind of makes sense, really. It's just you have to say it using using what is actually the natural language, which is sophisticated math. So if you don't have the sophisticated math, you can't. But once you know that sophisticated math, quantum mechanics just lines up and becomes pretty darn reasonable. So anyway, this is related, same kind of thing. Easy application. Here's a force and a displacement. How much work does it take if you displace by that vector while applying that force? And so, dot product, easy arithmetic. Okay. Let's talk about that other way to multiply vectors. We're talking about cross product. So it turns out that cross product is a little weird. It relates to another thing that's really weird, which is the determinant. And so I'm going to segue into cross product after first talking about determinant. Determinant, I'm going to segue into that after talking about another thing that it relates to, which is the idea of a geometric description of orders. So this is a kind of a long arc to get to cross product eventually, but some really neat stuff at the end. We're going to start off with the following simple question. I've got a pair of vectors in R2, very important, R2, only R2, not R3. Two vectors in R2, and I'm going to put them in an order. I'm going to say that this one is the first one, and this one is the second one. That's a choice. This is an ordering that I can put on that pair of vectors. Now let me note, I can take the exact same vectors, exact same two vectors. I could just put them in a different order, right? I could make that one first. I could make this one second, right? I mean, if I had names, I could write this as, V comma W or, W comma V. One is listed first, one is listed second. And what I would like to ask is there a geometrically natural way of describing those orders? So, well, look, one thing that would occur to you here is here I'm going bottom to top. The first one's the one on the bottom, second one's the one on top. So you might call this an upward ordering, right? You might call this one a downward ordering. That'd be one way to do this. The problem is that if you take that ordering, what if you turn your head slightly to the right and where neither one is, what if they have the same upwardness, right? That's weird. So then you might say left to right, or there's all sorts of sort of ad hoc patchwork kind of ways you could address that. But it turns out there's a really convenient way to avoid a lot of these problems in a way that ends up being mathematically natural. And what it is to talk about clockwise, counterclockwise. Now this is very relatable, right? Everybody knows how to read an analog clock, I think. Everything's digital these days, but I think y'all know how to do that. There, from first to second, counterclockwise. right here from first to second, clockwise. And turn your head all you want. So the viewer's perspective does not matter in making this designation. Okay. All right. So next question. What if you have, instead of 2 vectors in R2, what if you have 3 vectors in R3? So to rephrase this question, is there kind of a version of clockwise-ness, counterclockwise-ness? Is there a version of that in 3 dimensions? Hard question. Turns out there's an answer. It's called right-hand order. I didn't draw a picture because the picture is really hard to draw 3-dimensionally. So I'm just going to do a physical demonstration. Conveniently, I have my visual aid right here, right, my right hand. So there's a certain hand gesture that is used. The hand gesture is fixed and rigid, right? So this is not sort of optional. Here's the hand gesture, as I wrote here. Index finger parallel to your palm. Middle finger bending in the way that middle fingers want to bend. So, no fair. Don't do this. That's not allowed. It's mathematically disallowed. Okay. So, first finger parallel to the palm, middle finger bending the way it wants to bend. That gives me 2 vectors, right? And whatever, of the 3 vectors that I have, whichever one are the first 2, I can put my index finger in the direction of the first vector. I might have to reorient my hand to move my middle finger some amount one way or the other, but I can get that middle finger in the direction of the second vector. Those 2 vectors define a plane, and notice that the thumb of my right hand points on a well-defined side of that plane. So this plane here, there's that side and there's that side, right? And my thumb, if that's the first vector and that's the second vector, my thumb points on this side of that plane. Okay, so for that trio of vectors, we would say the vectors are in right-hand order. So here's some pictures, and these pictures are bad. But it's really hard to do better than this with a 2-dimensional piece of paper, drawing 3-dimensional vectors. So if that's the first vector, that's the second vector. That's intent. My intent there is the second vector is going into the page, right? And then the third vector pointing up. Okay, so this trio of vectors here, let's try to decide, is that trio, and in that order, 1, 2, 3, so that list, is this list right-hand order or left-hand order? Well, let's see here. First finger in the direction of the first vector. Orient my hand in whatever way I've got to do to get this middle finger to point into the page. Well, I have to do this. My thumb is pointing, in this case, on the upward side of that plane defined by the first 2 vectors. The third vector is on that same side. That third vector is on the thumb side, you might say. So we say that listing is a right-hand ordering of those vectors. Yep?
Are these like designations for the purpose of communication?
Yeah, it is for communication convenience in some cases, but it actually, in a way, is really hard to see coming. It relates to algebra. It does, and I'll show you in a few minutes. We got to kind of work our way up to it, but it is very important, in fact, in interpreting certain things algebraically.
So will there be like problems where it makes more sense to use this?
Well, there are going to be some questions where you do a certain calculation, you get a certain result, and you're asking, what does this result mean? And the answer is going to be, because of this, the way this algebra worked out, I can conclude these vectors are in a left-hand order instead of a right-hand order. And there's certain other theorems that say if you want a certain thing to happen, you need the vectors to be in right-hand order. And you got to make sure that if you're in left-hand order, that doesn't work. That kind of thing. Yeah, it's kind of weird, but you'll see. Yeah. Okay. Let's look at this trio of vectors here. Let's see here. First vector is going that way. Second vector. Well, now look how my middle finger is bending. That second vector is going into the page. My middle finger doesn't want to go into the page, so what do? Well, keep in mind, I can turn my hand around however I have to, right? If I turn my hand around that way, then notice I can totally get my middle finger to go into the page like that. Now my thumb is pointing down. The third vector in this list that I'm looking at is pointing up. My right hand thumb is pointing down. It would have to, that third vector would have to be pointing down below this plane, right, in order for that to be a right hand order. So this is not a right hand order. Not hard to persuade yourself, though. It's a left hand order. You can fill in the blanks, figure out what I mean by left hand order. Right. So, convenient. There is the kind of the in-between case, and that is, what if you have three vectors that are parallel? So it's kind of a sort of, so here's right-hand order. These vectors here are still in right-hand order, but then eventually, if all three vectors are parallel to the same plane, then it's not right-hand order anymore. But then again, it's not left-hand order either. So it's just kind of in between. So we say those vectors are coplanar or something like that. Okay. So some neat facts about right-hand order and left-hand order. In the same way that clockwise and counterclockwise are mirror images of each other, right-hand order and left-hand order are mirror images of each other. So the analogy between right-hand order or left-hand order versus clockwise, counterclockwise is pretty strong. Right? It doesn't depend on your perspective. You can turn your head around however you want. Right hands still look like right hands. Right? Just like if you look at a clock, you can turn your head sideways or this way or that way. Clockwise is still clockwise. Yes?
In the 2D space,
yeah.
You use any two vectors, right? And see.
As long as they're not parallel, yeah.
But in the 3D space, it doesn't have to specifically be perpendicular.
Nope. Any trio of vectors. So here's the rule again. The first two vectors, as long as they're not parallel, the first two vectors are going to define a plane, right? Your thumb then hand gesture according to the rules. Your thumb defines a well-defined side of that plane, right? If that third vector is in that same side of the plane as your thumb, then that's a right-hand ordering. If the third vector is on the other side of the plane from your thumb, that is not a right-hand ordering. It does not have to be perpendicular. Now there are different versions. There's a lot of things out there that like to call themselves, the right-hand rule or right-hand order. How, if you have a charged particle moving through a magnetic field, what direction is the force? Or other things like that. If you have a current through a wire, which direction around the wire does the magnetic field flow? And there are little games that you can play with your right hand on those. And some of them, something's perpendicular to something, and some of them it's not. This is a very general, this is just about vectors, and just trying to come up with a three-dimensional sort of analog of clockwise and counterclockwise. So in the same way that these vectors don't have to be perpendicular, right? Likewise, these vectors don't have to be perpendicular. Yeah. But I totally know where you're coming from. Yeah. Okay, here's some other weird things about right-hand order, and these are really, really useful to know. If you kind of take those three vectors and just kind of cycle them, kind of like cutting a deck of cards, you take the one that was at the beginning and move it over to the end, right? So ABC would turn into BCA, would turn into CAB. Those will always have the same order. That's a neat fact. Here's a kind of a demonstration. Are you all aware of this term, hand-waving proof? It's intended to be slightly derogatory. If you want to prove something, you should write down algebra, and it should just be, absolutely watertight and complete reasoning. And you shouldn't have to get up and make a barn-burning speech and wave your hands around and threaten, right, to persuade someone that what you're trying to explain to them is true. So a hand-waving proof is that's like saying, well, that's not a good. I think there's holes in your argument there, right? We call it a hand-waving proof. I'm going to give you a kind of a proof of this fact here that literally involves hand waving, and here it is. That's what cycling looks like. And you can see, you cycle the vectors, right? It's the same three vectors. You cycle them, and I can match them to my right hand by doing this. Yeah, I think that's funny, right? It's literally a hand waving proof. Yes.
So when, the way you determine the order,
Uh-huh.
you say that your thumb versus the other?
Mhm.
What does that mean? And how do you tell?
Well, this is just a geometric appeal, right? But if I have two vectors that are not parallel, they define a plane, right? Okay. A third vector, this third vector here that my stylus is representing is pointing onto this side of the plane. The plane cuts space in half, right? There is the what I'm going to, in this case, call the upper half. This vector is pointing into the upper half, right? This vector is not pointing into the upper half. It's pointing below the plane. So it's just a geometric appeal, right? We're defining this geometric notion of handedness, so I think it's fair that we can interpret it geometrically. Is that a happy face? I'm not sure. Are we good?
I'm still a little confused why
Okay.
if you look in the notes, the one on the left hand side is a right hand order. How would you?
This one here?
Yeah.
Yeah. Okay. Well, so let's do that one again. First vector, right? Now, with my index finger pointing in the direction of that first vector, I can kind of twist my hand around the axis of my finger, right? And do it in whatever way that allows me to get my middle finger now to point in the direction of that second vector, which is going into the page. These two vectors define this plane. My thumb is pointing that way, right? My thumb's pointing, what you might call, to the upside of this plane. So the upside is the direction that we're kind of hoping that third vector is pointing, and it is. So that third vector is pointing the same side of the plane as my thumb of my right hand, and so right hand order. Yeah. Okay. All right. Here's another sort of cute feature of right hand order. You take any list of vectors, if you kind of trade two of the vectors, that will always change the order. If ABC were a left-hand order, then ACB is a right-hand order, and vice versa. So swapping two vectors in the list changes the order. Cycling vectors, like cutting a deck of cards, never changes the order. Yeah, just neat facts about geometry. Okay, and this second fact, you can also kind of think, how would you go about proving this, and play games with. I think this would be a good hand demo of that fact. Right. So I'm switching the first two vectors, right? Thumb in the same direction. What had been a right-hand order is now a left-hand order. Okay. All right, so that's this order business. Again, surprisingly important. Now here's determinant. Remember, our goal is to talk about cross products. When we talk about cross products, I want to be able to talk about determinants because they're really useful. And when I talk about determinants, I want to be able to talk about order because that turns out to be really useful. So I have to sort of, again, there's a building process. Here's determinant. I'm curious how many of you all have seen this formula here for a 2x2 determinant. Show of hands. How many people know why that is the formula? Right. Okay. What they told me in high school was, if you're solving a system of equations, this is the magic tool that will allow you to draw certain conclusions. And well, that's other than the fact that it's an appeal to magic, that's certainly one of the neat features of determinant. Yeah.
Well, I don't know, but there is the way that you can solve any
Kramer's rule. You talking about Kramer's rule?
Where you take one in the top row and cross out the row in the column, and then do that times the determinant of the matrix of the other one. Yeah,
so that's what gives rise to this formula for a 3x3 determinant. Now, so what you've described there is a sort of a generalization. That generalizes a 2x2 determinant to any size matrix, and that's a great fact. We're not going to cover that fact, but all that does is further define determinant, right? So one of the things I want to leave y'all with is, why would we ever want to define determinant, right? What is it about this formula that we actually care about? Right? Okay, so, Math 216, we'll talk about that. Right. So here's the formula for a 3x3 determinant. Anybody seen this before? right? Similar, I assume, as to why. The big question students ask me all the time is, what's the deal with the minus sign? Right? Seems kind of weird to just stick a minus sign in there. Yeah, well, nobody ever complained about that minus sign. Right? It turns out they come from the same place as your formula that you point out, right? Okay, so maybe the question should be, what's the deal with all of these minus signs? And the answer is extremely deep. So I'm not going to be able to give you a satisfying answer for that. What we're going to do in Math 212 is we're just barely going to scratch the surface on determinant. I'm going to show you just enough about determinants so that we can kind of get some stuff done. Right? We're only going to talk about 2x2 and 3x3 determinants. Right? If you want to see more about determinants, come into Math 216. We'll spend like 3 lectures, or maybe it's a little more than 3 lectures talking about determinants. There's a lot more you can say. They're really very powerful constructions. That discussion of determinants is still a scratch of the surface. A really robust discussion of determinants is pretty darn hardcore, and beyond what you could do in an undergraduate class, maybe an advanced undergraduate class. So we're venturing into deep water here, and just be aware that a lot of the answers to questions you might have about determinant are, yeah, we can't talk about that right now. It's just kind of the nature of the beast. Okay, but yeah. So now, as a memory tool, you can think of this as going along the top row. This is the formula he was talking about. Note that each one of these terms involves an element of the top row, the determinant of the 2x2 matrix that you get when you cross out the row and column of that element on the top row. Okay. And then alternating signs, plus, minus, plus. Arbitrary rule. That, when chosen, gives rise to amazing, sort of like unexpectedly remarkable connections to geometry. So I'm going to show you what those connections to geometry are, but I'm not going to tell you why. Okay, so here's a start. Our first connection to geometry. Let's consider a couple of vectors. Right, specifically an ordered list of vectors, a comma b. So I do not mean the vectors a and b in whatever order you like. This is specifically an ordered list. A is first, b is second. All right, now here's a couple of things that from that list you can construct. On the one hand, you can construct a matrix. Notice that A is first, it's the first row. B is second, it's the second row. Not optional, you got to do it in that order. Okay. Also, A being a vector, B being a vector, I can do that. And that makes this parallelogram. So I've created, from this list of vectors, I've created an algebraic object, namely a 2x2 matrix. I've created a geometric object, namely this parallelogram. Okay. And it turns out, sort of weirdly, that these two things are connected. The determinant of the matrix tells you a bunch of information about the geometry of the parallelogram. Yep.
For this 2D version,
yep.
How do you determine whether you go clockwise or counterclockwise?
I'm going to tell you.
Okay.
Yeah. So, so far, first one first, second one second. Right. Okay. All right. So here are the 3 different possibilities and sort of a summary of them. You could take the determinant of this matrix. If that determinant is positive, then the area will be positive. Hang on a second. Like I said, I said that weird. If the determinant is positive, then this ordering, keep in mind, first one's first, second one's second, so this is, as I've drawn it in that order, this ordering will be counterclockwise. Positive determinant, that's an algebraically computed thing, means counterclockwise order. That's a geometric concept. Weird connection between determinant and geometry. right? And it goes the other way as well. So if you have a negative determinant, you have a clockwise geometry. Now, this picture is not drawn that way, right? I only drew the one picture. I wanted, A to be first, B to be second, and so anyway, if the determinant were negative, this picture would be the other way. It would be clockwise. Yep.
Does that statement work both ways? Like if you do A
Yes.
clockwise?
Yeah. Totally. These are if and only ifs. Totally. And then lastly, if the determinant is 0, then that means it means that the order is neither clockwise nor counterclockwise. And in the same way that 0 is kind of the boundary between positive and negative, likewise, parallel is the boundary between clockwise and counterclockwise. Okay. Also true, these relate to areas. So this area here, how much area is there in that parallelogram? That area is always the absolute value of the determinant, which is all these formulas. And if you think about it, if the determinant's negative, that determinant being the negative of the area means that the area is the negative of the determinant. It's the negative of the negative determinant. It's the absolute value of that determinant. Okay. All right. Okay, so nice summary is that if you have a couple of vectors, if you make a matrix out of them, the determinant tells you the area, and the sign of the determinant tells you the order, clockwise or counterclockwise. Okay, so example. This one's easy to confirm. I'm just going to leave it to you all to confirm for yourselves that this makes sense. But here's a couple of vectors. Right? And I can take those vectors and make a matrix and take the determinant. I get -5. What does that -5 tells me? That -5 tells me by virtue of come on, eraser. By virtue of the 5, tells me that area is 5. And by virtue of the minus sign, it tells me that this is a clockwise ordering. Yep.
But didn't you just arbitrarily put one vector in front of the other?
Nope. I very carefully put the first one first. Right?
Well, I'm saying, couldn't you just switch them?
I could have asked a different question.
Okay.
Yeah, I could have asked, I could have said, hey, what if 3-1 was the first vector and 1-2 was the second vector? But yeah, so in order for the question, hey, is this a right-hand order or a left-hand order? In order for that to make sense, I have to decide which vector is the one that I'm saying is first. I have to give a well-defined list. Does that make sense?
Yeah.
Yeah, cool. All right. Okay, here's the 3-dimensional version. You could probably guess, based on, hey, well, gosh, if stuff's going to work out, it seems like this is what it ought to be, and you'd be right. If you have 3 vectors in R3, you can make a matrix. You can make a, whatever this thing is called, yeah, that's right, it's right here. Yeah, that's right. That word's always struck me as weird. But anyway, you can make the corresponding geometric shape, you can make the corresponding algebraic construction, and the sign of the determinant tells you about the ordering of the trio of vectors. Did you list them, as ordered here? Did you list them in right-hand order or left-hand order? And it also tells you about the volume of the parallelepiped in the same way. Positive determinant means right-hand order. Negative determinant means left-hand order, etc. So here's another example. Trio of vectors. Now again, very importantly, that one is first. This one is second. That one is third. I tried to draw these reasonably to scale, reasonably sort of geometrically accurate. I think geometric appeal, but purple, blue, green, I think you can see that's a right-hand ordering. It looks like a right-hand ordering, right? What if it had been a completely different list of vectors where there weren't as many sort of, bunch of small numbers and just a few larger? What if it really wasn't geometrically obvious? Well, then you take those vectors, first, second, third. Take the determinant. You get positive 21. The 21 tells you that this volume here is 21, and the negative, the positive, positive tells you that that's in right-hand order. This is a right-hand order. Okay, yep.
You may have already covered this, but
Yep.
what's the reason or we should know the ordering? Like, what does it tell us about the just the way that
Well,
we use it?
what I'm showing you in this theorem is that if you know the ordering, you know the determinant's positive. Right? So you know this algebraic fact about determinants. Yeah. So, I mean, part of the reason that we want to talk about this, I mean, it comes up in physics sometimes and stuff like that. But part of the reason I'm indicating, I'm telling about order here is because it's this free information that's connected to determinant, right? I need to be able to talk about the magnitude of the determinant, the absolute value of the determinant, to talk about volume. I mean, I know we all know that volume is important, right? Well, the other free information is this order business. So I might as well give it to you. And I'm out of time again. Okay. We will pick up here on next time. Okay, see y'all later.